All right, good morning. We should get started. How we're more tired after break than before break. I don't understand how it works. But there's something. Man, I'm exhausted. Maybe I had too much fun on break. We were discussing the constancies in perception. Constancies are this weird collection of kind of consistencies of the perceptual system that, because we have them, we have a hard time noticing them. But if you were, again, trying to do like machine vision, they would immediately pop out at you. So we had talked about shape constancy last time, end of last time. And the kind of trivial example, it seems, is opening a door. So as the door opens into the room, your perceptual system keeps the shape of the door the same for you. You don't see the door transforming its shape, even though there is an interpretation in which the image that's projected to your retina would be exactly the same as the door opening if the shape of the door itself. And I realize it's hard to imagine. But that's the fact that you don't consider that as a possibility. You don't go, oh, look at that, the door is changing shape in front of me, is attributed to your perceptual system. And is probably what they're trying to describe when they say shape constancy. Okay, so it's the fact that you don't consider that as an option. Right? So we have these things all the time, and you can imagine. So let me go back to the computer processing metaphor. Imagine now that your job is to, over the transformations in the visual image, is to write a computer program, right? So you have the pixel map for this, you have the pixel map for this, and you have the pixel map for this, and your job is to say, oh, computer, identify that this is the same object, keep it the same object, despite the fact that these pixels are all very, very different from each other. So relationships in these pixels. See what I mean? Now it seems like a little harder problem. But for you, it's no problem at all. Obviously, you do it all the time. So that's shape constancy. We also do this. Try that and that. Yes. We also do this for things like size. The size of objects remains the same, despite the fact that they take up more and more and more of your visual field as they approach, or less and less and less of your visual field as they go away. Right? So here we have someone walking at a distance and someone walking up close, but we know that it's not the case that this guy is really small and this guy is really big. Right? That would be a weird interpretation, even though there is a sense in which we could have, if you were to kind of compare the absolute sizes of those images, right, it could be that there was a really little person here and a really big person here, right? So the problem that they're pointing to is, look, if you were to be trying to distinguish between two situations, somebody being at a distance and somebody being up close, right? Those are complicated by the fact that somebody really small up close takes up the same amount of space on your retina, essentially, as that same person at a distance. See what I mean? Right? If they were big. Right? So how do you know about size? Why do you keep it constant? Why do you not say that the person is shrinking and growing? Well, because that's not how the world is. But that's not a very good answer if you're trying to explain how perception works. Okay, so these constancies are a bit of a mystery and are really hard to solve kind of from first principles. Okay. We start to see other serious aspects of perception in things like impossible figures, where your system kind of strives to make normal sense of, in this case, cleverly constructed drawings that are impossible to implement in the 3D world. So this is a famous example. So what we have some sort of diagram here, and we have this piece has to go into this piece, and then you attach the bolts. Okay, so when you open up a package, this is not the diagram you want to see. Right? You'd be like, well, that's going to be interesting. So obviously the problem is that locally, this all makes sense, right? So this looks like here in this region, a two-pronged figure, a two-pronged item piece that's going to go into here. But then as you kind of follow this along, it suddenly turns into a three-pronged thing, but you can't quite identify where it does so. See what I mean? Kind of odd, very clever, right? Somebody really understands how to draw. Right? And so that's an issue. But then you also look over here, and this thing has kind of two interpretations going as well. One is that this corner is in the back, right? And this corner is in the front. Now it's flipping for me, so I'm having trouble, right? But if you look at it differently, this corner could move to the front rather than the back. See what I mean? So the figure's kind of unstable that way. Okay. So it would actually be pretty funny if someone were to include this in the instruction manual for how to put something together. But you see the problem, right? So those figures are impossible in the sense that you would never encounter something like that in the real world because your visual system just wouldn't allow it. But you kind of make local sense of it without being able to make global sense of it, which is interesting for people who do perception. This is another famous set of impossible stairs, right? Everything seems to work locally, right? But then you'll find that there are contradictions globally. So going up, well, that all makes sense. And then up will eventually turn into down, or a staircase that is going up here, you start up here, actually seems to be going down. So so these kind of figures are famous. You've probably seen them before online. And someone spent an awful lot of time figuring out how to do this. So these things have brought people to a two process globally idea about perception that is within this information processing approach. Information processing is probably the most popular still approach in visual perception. So a lot of what we've been talking about so far, we would consider data-driven, or what they sometimes refer to as bottom-up processing. The idea is that you get some set of inputs, right? This all comes in at the retina, goes to the ganglion cells, right? Goes through the optic nerve, and all along the way, little things are done, little things are computed, and eventually you end up with a perception. Oh, it's a desk. Great. So that's a bottom-up kind of story. Now that bottom-up story, as we've been talking about it, is kind of infused with the best possible solutions already. Right? It's already kind of got a bunch of knowing in there, a bunch of knowledge, we might even say. Some of it from learning, some of it from kind of predispositions of the system. So it's not like it's computing anything. It's already very, very smart system tuned up for this environment, let's say. Right? So we have input, and that goes to knowledge in the sense that perception provides knowledge about the environment. But we also have top-down processes where we go from the knowledge, and that kind of constrains what's happening in the inputs or how we interpret the inputs. So they want there to be another set of processes as if the whole thing were a network that kind of is boiling up from the inputs, but also boiling down, not a bad metaphor, but in a way so that the possibilities, what I know about what could be happening right now constrains how the network kind of settles out. And when you put it that way, it's a little bit less mysterious that there are, the network both goes from data to solution, right? But it also goes like from current state to solution a little bit. You know what I mean? So the knowledge having an impact down is the top down. Let me give you some examples that will make it maybe a little more clear. So this is a perennial favorite, very, very simple one, but very powerful because you really almost can't help but do it. So as experienced readers of English, this very quickly resolves to the cat for people, right? And you wouldn't even necessarily notice that there's anything weird about it if it were just flashed at you, right? You just go, well, it said the cat. What are you talking about? So obviously, probably, the problem is that the letter H here in V and the letter A here in cat are exactly the same. But as a reader, you took them to be entirely different because you have knowledge of what are acceptable letter combinations in English, right? And they're very powerful for you. And they immediately organize this into one word, which mandates that that has to be an H, and this into another word, which mandates that that has to be an A. So that's a great example of top-down knowledge of English, right, which isn't, you know, in any sense a like evolutionary level pressure on you. Has immediately organized this letter into one thing and this letter into another. And in fact, you know, clever psychologists, what they do, right? They give people this sort of thing and they say, well, can you just show me what you just saw? And people will very clearly write out THE and CAT, where these things don't look anything like each other. One looks like an H and one looks like an A. So things like that are great examples of top-down effects. You get the same sort of thing here, where this looks like A, B, C. In this case, that same figure in the middle looks like a 13 in this case. And neither of them looks particularly weird. Right, so the same kind of argument applies. Right, so again, the idea is that your knowledge of and expectations actually are running perception, not entirely, but to some extent. So this perceiving the world, it makes it challenging for us to know how you actually, like, how do you then come in contact with the world, right? If your knowledge is sort of interceding once in a while. Okay, questions about top down, bottom up, or the constancies before we go on?
How does the constructionist approach fit into all of this?
Great question. So the question is, how does the constructionist approach fit into this? This is very much the heart and soul of the constructionist approach. So this stuff up here, this mystery of how knowledge can be both the product and kind of part of the solution itself, spent an awful lot of time on. Yeah. So this is very consistent with the constructionist interpretation, because now the best solution is being, right? So remember, this is the Helmholtzian stuff where we're like trying to get the best solution given the data. Well, the best solution now isn't just given the data, it's given what I know. Okay, so very much in the constructionist way of thinking. Other questions? Okay. So sometimes you talk about this as context effects. One of the great poorly defined and often used words in psychology is context. Basically, it means that there are a whole set of variables that we don't have a good handle on. We'll talk about them as context. So here, context is, well, essentially like the flanking letters in this setup are context. And those draw upon your knowledge, organize things a particular way. They have context effect. We're going to take now a step back away from the constructionists and talk about a group called the Gestaltists, which actually they were a group that started in Germany. As World War II started to show itself on the horizon, a lot of them moved over here and were kind of East Coast academics. They came over here and we were like in the midst of the early parts of behaviorism, a little bit of structuralism, and these guys were like from a different planet conceptually. And because the world was kind of bigger then, in a way, it was right, it was kind of more separated. These people were not particularly well known to each other, not like today where everybody sort of knows everybody. So one way to think about Gestaltism, I'm not sure it's a very good way, but it's said a lot, so I'll put it up there, is that it was at the time another form of nativism, which is to say that you perceive things as you perceive them because evolution required you to. And you're carrying around that requirement in your, we would say today, in your DNA, and that has made you this way. And so you can think about them that way. It's not terrible. I think of maybe a better way to think about them, without putting too much modern spin into it, is they were interested in the dynamics of the brain. Were super hard to measure back in the 50s, 60s, 40s, 50s, 60s. But that's where they thought all the action was. And they had this idea that perception is essentially this big brain network settling into solutions. Hard to argue with. In today's world, we go, yeah, something along those lines. That's pretty good. Right? But, you know, that's nice to say, but what do you do with it, right? It doesn't imply the next experiment. It's like, well, it's a network that's settling into solutions. What they did with it was to say we can actually find the tendencies of the network in the visual world at least. And we're going to name those tendencies as rules, or sometimes we call them laws. So what they ended up doing, even though they're interested in this dynamics explanation, they ended up coming up with a whole set of laws. And they're not laws like the laws of physics. They're laws like tendencies to organize a particular way. And then you'll see that they're very descriptive, and they're interesting, but they're not really explained by calling them laws. Okay, they're like summary statements of what happens. So their story kind of goes like this. We have the distal stimulus, right? The actual item out there in the environment, in this case, a tree. We then have the proximal stimulus, which is the light reflected off the tree through the lens and so on and so forth, right? Which is impinging on the back of the retina. Okay, so far so good, nothing new there. We then take this distal stimulus and we have these laws of organization, as I just described them, more like dynamics of the network that give rise to these normal things that happen. Okay, so that's what we're calling your inborn laws of organization. And the result of that is your perception of, your knowing about the state of the world distally. And so way out here, now we know that given this proximal stimulus combining with the laws of organization that I am carrying around with me as part of my perceptual system, I now know that there's a tree. That's the general story. This fellow, Max Wertheimer, was one of the founders of this field. And these laws of organization are supposed to be responsible for creating your perceptual experience, and they set about then to try to name them. Right? Kind of like, zoology, except now we're trying to figure out what the elements, what the laws are in the perceptual system. So to do this, they did a few things. They discovered a bunch of really neat illusions, which are fun and interesting to look at. And then they just discovered other things which aren't so much illusions as they are just kind of weirdo tendencies that your system has. And I'll show you some examples of both of these. This is a famous illusion. I think I showed you an example of this earlier. This is the Panizza square and the Panizza triangle. The illusion is created entirely by the presence of these cut out circles being oriented in a particular way. And there's no sense in which there's an actual square there. There aren't hidden lines. It doesn't. There are no tricks. You can make one of these. You can do this in PowerPoint in 2 minutes, and it would work for you. And the phenomenon goes like this: you kind of perceive a square here as if it were sitting on top of these circles. And in fact, one phenomenon that a little more subtle, that the more somebody describes that to you, the stronger the illusion can get. That may be happening to you right now. You're like, oh, now would you say that? I see that a little bit more. The brightness of this area here, which is the square, tends to be greater than the brightness outside of it. Right? Perceptually speaking, of course, not. There actually isn't a brightness difference in those values of white that are being projected onto the screen right now. Right. So that's the illusion. For them, they say, well, that just comes right out of a set of organizational knowledge. And I'll tell you what the set is in a moment. But that's just how it is. That's what your perceptual system does. You get an even stronger sense here because there's kind of more stuff implying this edgeless triangle here. There's a triangle beneath it. Sort of interpretation. Right, so these guys are, all right. Sure why that suddenly decided that was important. Let's see if I can make that guy come all the way over. Drop it. There. All the heck with it. We'll leave it there for now. Anyway, all right, so let's back to that guy. So these things are sometimes called subjective contours. And they created these things to show how perceptual experience involves these laws of organization. So really isn't good, is it? Oh, crud. See, maybe this guy will help me. Okay. Sorry about that. Quite sure why I did that. Don't know what to say about it. Being defeated by the technology. Goodness. Okay. So, for example, here is a law of organization in which we see the set of lines as 3 pairs of lines when we don't necessarily have to. Right? It's super simple. It's so simple. It's kind of trivial. Right? It's like, why would that be interesting to people? But you can see that you can change that up, right? So this particular setup doesn't favor another organization, which could be, right? Now I'm just color coding them to show what is not being favored, right? So it could be your perceptual system could have split things essentially here for the first 3 lines and the next 3 lines, but it doesn't, based on sort of the proximity of these things. Right, and there are other configurations as well, right? Again, the color coding just saying, well, these things could have gone together, but didn't for your perceptual system. So the proximity of things, that is things being closer to each other, for some reason tends to organize them for you, right? It turns it into pairs when it could have turned it into many other possibilities. Okay, very, very simple point. Another illustration. So we tend to see this as alternating columns of figures. That's a favored interpretation. There are other, again, the color coding just showing you that these things could exist. So you could have seen things here as 2 columns being together, and then another pair being together, and then another pair, right? You could have, but that's not what pops out at you. Right? Likewise, you could have seen rows instead of columns. There's nothing illegal about that. But again, because of the way that those elements are, how they're arranged, what they are, you just don't do that. So this is sometimes called the law of similarity. So why similarity? Well, the things that are similar are put together. That similarity forces you into columns rather than rows or rather than groups of columns. We usually would see this as intersecting curves. So a curve here and another curve here. But again, you don't have to see it that way. Logically speaking, it could be a lot of things. So again, you could have seen it as kind of a discontinuous curve here and a discontinuous curve here, but you just tend not to. So for them, again, these are kind of properties of the dynamics of this network. They tend to deliver these kind of solutions to you. Now they've named them into laws. All right, so there are other ways you could combine that as well. They call this the law of good continuation. Now you might ask, well, what makes one continuation good and another one not good? It's a hard question. Right? That they would say, well, that's just the way it is. Some things are good continuation and some things don't. So whatever the system favors is what I'm talking about. I don't need to kind of define it mathematically or anything for you. You could talk about, like the smoothness of these, right? Everywhere differentiable or something, and maybe that would satisfy it. But generally, these things aren't like from first principles. They're, again, summary statements about what happens. All right, so here are 3. Law of proximity, things being close together tend to get grouped together. Law of similarity, things that are similar tend to get grouped together, and that creates kind of things hanging together that don't necessarily have to hang together. Likewise, the law of good continuation says, look, when you have intersecting surfaces, you tend to go with what's likely, what's smooth, what's nice. So in general, the perceptual solution that perception settles on is following these laws, and in a way you can give them an overarching name. They tend to call them the laws of simplicity. And the laws of simplicity, these are examples of some of those laws, describe what it is you do when faced with the world. And you do this all the time, is their argument. Okay, it's one way to try to approach a problem, and it worked to some extent. So those are laws of simplicity. They like the word laws a lot. They also have this thing called the law of prognance. So prognance here means that we're always trying to reduce reality to the simplest form possible. So we're always trying to make the simplest story happen perceptually. And in doing so, we kind of invoke these laws of simplicity. Right? So there are kind of two overarching things. One is the description of the laws of simplicity. We've had some examples. And then this law of prognance, which essentially says, when possible, always simplify. Go with the simplest possible story. So you can see that kind of at work in each one of these examples. We tend to see this as two figures, a triangle and a square. Of course, it could be anything, right? It could be how these things are connected in reality. I mean, imagine these are pieces of iron that you're seeing from a particular angle, like one of those iron puzzles, where you have to twist them around. You don't know that it's a square and a triangle. It could be a lot of different things that are connected, right? But that's how we tend to see it. Here, similarly, we tend to see kind of a bench in the back and a kind of monolith here in the front. Again, you don't necessarily, there are other interpretations available, but that's what you tend to see. Likewise, this we tend to see as like a set of overlapping rings, but we don't know that they're rings. Your visual system just organizes them into such a thing. So there are a bunch of other laws. I'll just name a couple because they're ones that you see all the time. So closure, you tend to assume that all curves are closed even when that closure isn't visible. So here we assume that the panda bear's head is a closed figure, even though there's no edge between the ears. All right, so that's the law of closure. Even when we can't see all of the edge, we assume the edge exists. We also tend to go for what's called common fate. So here's an example of some dots. Right now, they're just dots. And them being dots is not particularly interesting. And none of the laws are like really coming to our aid here. We're not going, oh, I see something now. But as soon as we start them into motion, it tends to jump out at us what this is, I think. For a lot of people it did, at least when they did the research way back when. Right, so this is, get back to that guy. Oops, I'm going the wrong way. I tipped it apparently. So obviously it's a human walker, right? Does that seem obvious to people? So these are called point light walkers or point light displays now. It turns out that with just like information about what you're doing on a few of your segments, you don't need to need all your segments. And by segments, I mean the rigid parts of your body, right? So you can put a marker here, a marker here, right? A marker here, a marker here, right? So they have different degrees of freedom, right? You can see just out of the pattern of motion, like what somebody's doing. So here they're walking, but they have there's actually, if you go online, you'll find this point light displays or human point light displays, maybe. They have a whole bunch of these things. And they have taken essentially the dynamics of people doing things. So you can see somebody raking, right? Or somebody sweeping the floor. And you go from a set of dots like this to a very compelling, like, oh, I know exactly. They're lifting a glass. So all those things are given by the point light display. What the Gestaltists would say is that's because things which are moving together, you assume are doing so for a reason, and that's this common fate idea. So things that tend to be changing together, you assume are changing together because they're physically connected, and that allows you to make an inference like it's a person walking. All right, questions about the Gestaltist before we go on?
How is closure any different from subjective contours, like the book?
Yeah, yep, that's a great point. So subjective contours are the experience of seeing it. Right? It is a phenomenon. Closure is the law in itself. So that's why you see subjective contours is because of the law of closure. So subjective contours aren't themselves a law, it's a phenomenon. Other questions? Okay. So we have been talking about perception from this very traditional, what is sometimes called Helmholtzian perspective. There's a distal stimulus, there's a proximal stimulus. That gives rise to a set of sensations. So because you have energy impinging on your sense organs, you get sensations. The sensations aren't meaningful yet. They're just a bunch of neuronal firings at this point. There's no inherent meaning in them, which seems like a sensible thing. You then have a bunch of associations, maybe cues, or maybe in this case of the Gestaltist, some sort of innate rules that are saying, well, that's that and that and that. We're going to get together. We're going to start to build some things here. Eventually, this is going to give rise to some sort of incomplete, kind of sketchy percept. Right? You have a internal sense of what's happening, but it doesn't fully specify what's going on in the world. Okay? And this we sometimes talk about as an incomplete percept, or a fellow by the name of David Marr made very famous this idea of having like a 2.5D sketch. It's like a rough sketch of what's happening. Right? So all this is supposed to be happening super fast in your brain. And then in comes the Helmholtzian unconscious inference process. That would be the constructionist viewpoint. More modern terminology would be like information processing happens. Oh, okay, I've got this thing. Now I need to figure out what it is. So I'm going to do some top downs or bottom up processing. I've already done a bunch of bottom up processing probably. Or if you're a Gestaltist, you say, in come the laws of organization. I'm going to put everything together for me, and these little fluctuations out there in the world, right, my little bits and pieces of my sketch are going to get put together. And I end up with real perception where I go, oh, it's a tree. Not only is it a tree, it's over there. I have all sorts of knowledge about it that is suddenly revealed to me through this process that is sometimes called epistemic mediation. Okay? Where that means mediation by knowledge. You now have the knowledge that you bring to the table comes into play, and you understand what the meaning of this minimal sketch is. So the point here is that all three of these different approaches, if we take Helmholtz to be one, modern information processing to be the other, and Gestaltist to be the third, just maybe a little bit of a funny, but stick with it, require this kind of epistemic mediation. There's something in between that's saying, now here's what you know to make a decision about what's there. So I'm now going to say, well, maybe some of this isn't necessary. Because this is all turning on the idea, crucially, that that perception is a problem because the proximal stimulus is inadequate somehow. It doesn't really sufficiently say tree to me. And it says a bunch of things, but they're not, it's just not enough. Right? And so all this stuff, and especially the epistemic mediation, is kind of filling in the gap, saying, yeah, given how things are going, it's probably a tree. Right? But what if that's not right? What if the information in the world is sufficient to tell you about what's going on in the world? Be a whole different way of thinking about things. And that's what I want to talk about in this last little bit here. So because we don't have adequate proximal stimulation, right, this does not specify that exactly, we end up having the brain or the mind or whoever it might be in there having to reconstruct the world for us. All right. But what if we assume that the stimulus information can be like adequate and informative and actually tell you about the world in and of itself? So this is the possibility that we're considering now, right? So we're kind of starting again with the problem. Saying, you know what? Maybe we got the problem wrong. Maybe it's not inadequate information. Maybe it is adequate. What would that look like? And what would we need? So let's return to the cat, the weird cat. All right. So here we have this figure of a cat. And our usual interpretation, right? The most likely interpretation, we thought perhaps, was that there's a cat in front of a background. But of course, there is this other possibility here, right? The cat, this figure is being created by a shadow of a cat, right? Where the light is on the outside and the background is back. So it's a cutout of a cat. Okay. Weird starting place for thinking about perception. You can see they're trying to simplify things. Right. So these alternatives are sort of the beginning of the problem for the Helmholtzian view, because look, I have these alternatives and the actual proximal stimulus isn't distinguishing them for me. Right? But what if the universality of the Helmholtzian heuristics, the fact that these things seem to work everywhere, are there because there are like lawful relationships between what's going on in the environment and what's going on in the perceptual system of whoever it is that's out there doing the perceiving. Okay. So this would start the whole thing over again, give us a different view of perception. So this work came out of work right again, also around World War II, by a fellow named James Gibson, who was studying how people land airplanes and the information they use when doing so. So what this is meant to show is an airport runway as you are on approach, right? You're looking out of the front of the plane. You actually can do this now in your seats, right? Oftentimes there's a camera located at the front of the plane. So you're on approach, and what he's trying to show here is that there's a flow optically as you make the approach, and that's what all these vector arrows are meant to show, right? So the longer the arrow, the faster it's moving. With me? The faster that area is moving. So things here are moving really fast. Things out here are moving less fast, but it's all absolutely systematically related to the process of landing the plane. Right? So if what you're interested in is landing planes, what you want to do is say, well, the thing to pay attention to is this, what he calls optic flow field, as you're landing. So it sounds very technical, but you can have the same experience to some degree by looking out the side window of the plane. Maybe you have had it, right? Everything seems to be going well, right? Oh, we're going to land, right? And then as you land, suddenly things go from being like incrementally, almost linearly getting closer So a sudden like expansion of the ground, and it can be a little bit alarming, but it's like visually guaranteed. So that's that kind of information, the optics suddenly expanding, like specifies the moment of landing. So that's kind of the inspiration for what he's talking about here. We can, and it's a little bit anti-Dixonian, but we'll go through with it anyway. We can show this with our silly cat example a little bit. And the idea here is that not just when you're in an airplane, but generally motion, being in motion like you always are, makes information happen about the world. So is this an object or an opening, right? That is a cat or a cat-shaped hole. Well, if the thing is moving against the background, well, then it becomes obvious. There's no question, right? So the motion actually is creating information about the thing, right? And you're always in motion, right? So both cases, the cat and the, whatever we'll call it, the cat cutout, are completely specified as soon as there's any motion against the background. Right? There's no ambiguity. And so he would take cases like this and say, well, that's ridiculous. When was the last time you had a 2D cat flash in front of you? It doesn't happen. In the real world, the cat's there. You move your head, the cat's still there. They moved against the background, or the cat moves. It moves against the background. It specifies itself exactly. Pretty good argument, right? So that's the beginning of these arguments. So he basically called for this a re-examination of the ambiguity idea that's at the heart of Helmholtzian and these other approaches. All right. So what about the perception of motion? And I'll end with this a little bit. So this goes back to the airplane idea. So here's the thing. Any displacement of the point of observation relative to the environment gives you information about motion. So for example, if there were a person running, all right, this person is coming towards us, that motion, right, so imagine that you're running, okay, I'm not actually going to run into the wall, but I'm running towards the wall. That motion generates optical information in the form of optical outflow, right? So the wall literally, that's what these vector fields are meant to do, expands in front of you. And that specifies the motion towards the wall, that you are in motion towards the wall. So by doing it, specifies it visually for you. Right? So the motion generates the optical flow specifies the motion, that the motion is happening. Right? So as he runs forward, you get this global outflow. Now, if you were to do it in reverse and run away from the wall, you would have global inflow. Right? So this is a simple example, but you see kind of the principle here is that by moving, either you moving or the world moving, you create information about what's happening in the world. Right? So here we have information being created about the motion by the motion. Likewise here, right? They're opposite in value, essentially. One is global outflow, and the other is global inflow. Now, there are other things you can do, of course, like turn your head, that also specify a particular set of optic transformations. And those two seem to be information about what you're doing. All right, I have to let you go there. Thanks very much for your attention.